Bem-vindo, pessoal do YouTube. Essa vai ser uma palestra em inglês, tá? Então, agora em diante, todas as falas serão em inglês. Welcome, everybody. Welcome, YouTube people. This is our first English seminar of this year in our traditional seminar series. So we're very pleased to receive this talk from Professor Israat Haque. Did I say it correctly? Thanks. And I will let Alberto say a few words to introduce our presenter of today. So please welcome Alberto, and afterwards Professor Israat.
Okay, so good afternoon. I'll just read a short bio. So Dr. Israat Haque is an associate professor at Dalhousie University in Canada, where she leads the Programmable and Intelligent Networking Lab. Is PINET or PNET?
PINET.
PINET. She has expertise in distributed networking systems and security, and she's developing high-performance, secure, and dependable systems for artificial intelligence, machine learning, big data, cloud, telecommunications, and IoT. And she was recognized as an ACM IEEE N2 Women Rising Star in 2021. And then she received the Digital Nova Scotia Thinking Forward Award in 2022 for her training the next generation of tech talents. And finally, in 2024, she received the Alumni Honor Award from the alma mater, University of Alberta. So, Israat, thank you for coming. The floor is yours.
Thank you so much. Okay, good afternoon. Hello, everyone. Thanks for inviting me, and I'm really happy and honored to be here. And today I'm going to talk about my current research project.
I'm sorry to interrupt, but it seems that the connection might have been lost. I'll give you a cable if you have the adapter to use, because perhaps this one would work. We have a cable. Does it have a network connector input? No? This one has one, so I'll give you. Perhaps we'll have a more stable connection. Try to go back to the conference, please, to the browser where you're connected. I think you have to share your screen again. Sorry for the interruption. I think if you change to the presentation, it might appear now. Is it the case that only the browser? Yeah. Okay, it seems to be working now. Yes. So sorry for the interruption. I think we'll be up and running now.
Okay, great. Yeah, so today I'm going to actually briefly share what I'm doing in my research lab, PINET. And title of my talk is The Role of Network Programmability and AI in Distributed and Networking Systems. So I'll be talking about two aspects. that how network programmability can be used to develop some distributed and networking system solutions, for example, for security, for performance. And then I will show that how AI can be used for the same domain. And finally, I will just bring one last point of making AI system that's sustainable. That's what I'm doing right now, but also how to make it secure. That's my future work that I'm planning to do. So this is just an overview of what's going on in my lab right now. These are the main three projects. The first one is using network programmability for IoT and cloud computing in terms of secure and high performance solutions. And I have presented here a couple of key projects. Quarago, which I'll talk about, is a security solution. Spotlight, another security solution. And P4 Howler is basically a load balancer that we developed in data. So I have multiple collaborators, both from industry and academia. One of them is UFRGS, Professor Alberto. The next one is basically AI for 5G, 6G. I'll show how we use that in that domain. And finally, systems for AI and big data. I'll just bring a couple of examples. So before I jump into my project, I just want to bring these key milestones from both network programmability and AI. And we are all aware of that, AI is right now really a hot topic, but the concept is not like new. It was a long time before, but if we can think of like modern AI, then I started from this 2012 when this CNN model AlexNet, that was the one first came up. And then the next milestone is, as all of us we know, is Transform 2017, the paper that was proposed, attention of all implementers. And then we have seen that how it transformed the entire world. So that's like the, another big milestone. And recently, of course, 2021, Delhi was proposed, and then now we know that what's going on in terms of OpenAI and other generative AI tools and techniques. In 2024, Geoffrey Hinton from University of Toronto, he won this Nobel Prize for his contribution. So these are the big milestones from this AI. I said modern AI because I started from 2012. On the other hand, if we go to network programmability, then 2008, OpenFlow was first proposed. And then in 2014, P4 language was proposed, which we call it's basically for protocol agnostic development. It's not confined by existing protocols. So that was another leap forward, moving from control-based or controller-based deployment to this data plane-based deployment. Now, then what happened is basically in 2024, because sometimes people say that, oh, okay, SDA and OpenFlow and network programmability is out of date. It's not much. And then, of course, I don't agree with that. It's going on. And then last year, even a company called Oxid, they took initiative to reproduce OpenFlow, P4-based switches. It's not like exactly Tofino, but like P4 and other P4 supported switches, they started bringing it market again. So it's not like, it's dead. It has still a lot of potential. There's a lot of activities going on across the world. Particularly, I feel that UFRGS is one of the most active universities in this network programmability, data plane programmability domain. And in 2024, in SEM SIGCOMM, this P4 paper got the Test of Time award because of its contribution, global contribution. So this is just to show that how these two domains are evolving. And now I will actually talk about that how I actually leverage these two domains to different types of capabilities to solve problems in my particular domain, networking and distributed domain. Okay, so that's the whole idea today. So first, I will present a couple of papers from security domain, show how I use network programmability to develop security solutions. So the first one is a system we call Quad.io, but let me just give a little bit of context why we developed that. So this system that we developed, we focused on smart home IoT devices. And especially in North America, as you may know, that on average there are 7 household IoT devices in North America. It's very popular. But as soon as you bring it online, of course, you create new attack vectors, right? We know different examples, like Mirai botnet, for example, how it actually took control and then impact our communication systems, right? So one solution in that aspect is that once we have these IoT devices, we can start monitoring them. Check what's going on, what they are doing. If there is anything unusual, then you can take some measure. So this monitoring, we call it like, fingerprinting IoT devices, meaning that identifying what type of device are there, what type of events are happening, and even like manufacturers or vendor, and then based on the outcome, we can actually take some measure that if there is something unusual, service providers can actually take some measures, right? So they can actually update their firewall rules or configure their intrusion detection systems, so on and so forth. There are many works actually. It's really actually a hot area, IoT device fingerprinting. For example, the ping pong. It's one work that basically showed that IoT devices, when they are set, they communicate with their backend cloud providers by exchanging messages. They say device triggers one message, ping, corresponding server reply, pong. Ping pong, there is this ping pong kind of communication, and these communications actually being used for various control purpose, and also when there is some event, there is this message exchange happen. And what they have done in that work is that, okay, can we actually capture those ping pong type of communication to fingerprint an IoT device? And once we fingerprint, okay, then basically we can use, let's say, machine learning model to analyze network traffic and see if we can identify that fingerprint and say that what type of device, what type of event, so on and so forth. Very neat idea, right? But the problem is that those are offline solutions. And when it comes to volume, we are talking about really large volume of traffic. Think about a neighborhood with many houses with many IoT devices. And these offline systems, they actually cannot cope up with high traffic volume. And you can see on the top right that once we increase the traffic rate, okay, then basically you see that their detection accuracy quite drastically drops. Okay? They cannot. To cope up, sometimes they do like sampling, aggregation, so on and so forth. But these devices, IoT devices, they do not continuously exchange traffic. It's like very seldom. So if you do some sort of sampling, there is a high chance that you will miss some, right? So existing offline solution cannot do a good job. So, but like ISP, if they want to monitor traffic in real time, in larger scale, they need to think of some alternative. What is that alternative? That alternative is our system Quad.io using network programmability. So we implemented this solution in ISP switch or router, and then you can check like every single packet and then tell in real time what's going on. That's the whole idea, motivation. Okay, so it's basically in-network IoT device fingerprinting, and we implemented it in Profino Switch. Okay, so and just quickly, why we name it Poirot? I think many of you know, like Poirot, this detective character. Since we are talking about security, so we inspired by that name and then came up with this name, Poirot.
I think they're too young.
But yeah, that's a good point. So this is the Poirot architecture. It has two parts, controller and then data plane, where we implement this Poirot's packet processing data plane components or packet processing pipeline. Now in the controller does three things. First of all, as I mentioned, that we need to first generate those signatures. So that's the thing Poirot controller does. It can be even offline based on something like ping pong, doesn't matter. But then once we have the signature, then we need to do two things: DFA creation, rule generation. I'll quickly talk about that here. What does it mean? Once we have signatures across multiple devices, instead of have like individual signatures as like finite state machine or deterministic finite automata, we actually put them together, created one DFA just to reduce the space requirement. Okay. Here is like one example. We have two signatures that we have generated, and we start with the state 0. If there is basically certain packet length coming from a certain direction, then basically we make transition. That's the whole idea of Poirot, because we said that we have these signatures. How can we detect those signatures in data plane? We have to have something like effective but not very complicated solution, because it's not very easy to implement complicated solutions in data plane. And we found that we can actually use only the packet length and direction to do that. So that's why we are using C, means the packet is coming from client, 211 its length. When we are in a particular state, we get the expected packet length and the corresponding direction, we make transition to the next state. And by doing so, we eventually reach to the final state and then tell that, okay, this is the event, right? And in that final state, we can, depending on what's the outcome, we can report it to network administrator to take further action. Now, once we create this DFA in controller, then of course controller needs to configure match action table in the data plane. That's what is happening in the right-hand side. So we are in current state. If we have the expected direction and the length, then we actually take the action of moving to the corresponding right state. And that's how we move forward. So this is like what controller does. And in the data plane, what happens is basically when packet comes, then it checks what's the direction, what's the length, and if everything matches based on this match action table, then it basically updates the state. And then once we reach to the final state, then it can actually generate some sort of report. So we evaluated this, as I said, by implementing it in real Profino device using real IoT traffic, and we could actually detect all the IoT devices that we tested, and also we could detect pretty much all events, and then reported that okay, this could be a good solution to monitor your smart home IoT devices. So the paper is already there, and then this is the Git repo link. If you are interested, be our guest, check what we have done there, and then share your thoughts, comments. So that's basically Poirot, IoT device fingerprinting at line rate in real time. Next thing that we did is considering advanced persistent threats. Now we are talking about threats that are basically long-term plan. Attackers basically target a particular, let's say, organization, compromise a particular, let's say, insider device, and then through that foothold, get into the targeted environment and spread to some sort of harms. And it can actually create really, really large damage. So I have brought here a couple of examples. First one is in 2015 Ukraine power plant attack. And we know that one happened like recently, some power outlets, who knows, could be like, this APT attack. The other one happened in my region in Canada, not exactly in our province, but the province beside us, Newfoundland and Labrador. They actually suffered from this APT attack. And traditional perimeter-based solutions like firewalls, IDSs, they are not very effective here because, as I mentioned, that usually using some sort of, let's say, social engineering-based attackers first compromise insider devices, and using that compromised device, then they start, getting inside, access unwanted resources, so on and so forth. So this is just a pictorial example that, let's say, you have deployed some, internet-facing servers in your DMZ, and then you are actually protected them using firewalls. But if attackers can actually compromise that insider device that you trust, then they can actually from there can create some sort of subsequent action. So, for example, like here we're saying in step one, this HTTP request, and from there actually the subsequent request, they can actually use, let's say, SSH tunneling or like socket-based attack or chisel-based attack that actually you can do without even having good reviews. You compromise that attack, and through that you can create, like let's say, this tunnel to target sensitive server and exfiltrate information. You can do that. And some characteristics of this type of attack is basically their time and their length. Again, very similar to Poirot. Usually when this sort of attack happens, of course they happen like as soon as it starts, it happens within certain time frame. And since it's basically because of like, you initiate one attack on the target device, which we call pivot node, by the way, on pivot node, because of certain request, there should be corresponding outgoing request to exfiltrate information. Because you compromise this pivot node, so now attacker actually inserts some sort of request, like let's say to the pivot node, which is your incoming flow, and incoming flow will create a corresponding outgoing flow, and these two incoming and outgoing flow, they have some sort of, correlation, okay? Causality, basically, you can think of it, that, basically the outgoing flow happens because of this incoming flow, and this entire activities happens within certain time frame. So there is a causality in terms of time and size. So we try to exploit that characteristics of APT, adverse persistence threat, and then come up with a system called the spotlight. What the spotlight does is that when every time like packet comes, of course we can identify flows in data plane based on 5 tuple, and then what we do is that when packet comes, we record in time, and then this time we actually pass it to the controller. We give it to the controller that, hey, this is the candidate flow we want to actually compare and check with other relevant flows within certain time window. See that if it is a potential pivoting attack. So we pass it to the controller, and then later on, when we actually identify in the data plane other flows within certain time frame originated from like that pivot node, then basically we need to compare that original first flow with the subsequent other relevant flows within certain time frame. We want to actually compare whether they are within this certain time frame, and they are because of incoming flow, and then immediately within certain time there is an outgoing flow. It's basically, then we can tell that there is something going on in this region. So our controller is the one who is responsible for doing this grouping, that which flows we are going to actually compare against each other. And the data plane is the one responsible for actually identifying flows, identifying the time, and then doing this comparison based on the match action table that basically our controller does. So I don't want to go all the nitty-gritty details. Again, the paper is there. You can check. I'm just trying to give like high-level overview. We again implemented it on Tofino using two real data. One is this Maui data, another one is CIC data, and then tested 3 attacks: Chisel, SSH attack, and SOCAT. And then just to show that we are doing good job in terms of detecting those pivot attacks. So those 2 examples using network programmability for security. Now I will quickly illustrate how I can use network programmability for performance. Okay, and in this case, we are talking about implementing or developing a load balancer. Okay, and this load balancer, which we call P4 howler, is basically, again, we implemented this load balancer in data plane on Tofino switch because of its ability to process packet at line rate. But the novelty of this work is that when we dispatch load, let's say AI inference, we dispatch it to data center across multiple servers. Usually what happens is that this middle box load balancer, when it receives this request, it dispatches to different destination server, right? Doesn't care that what type of resources that server has, like CPU, GPU, accelerators, and what's the state of those computing resources, it doesn't care. What we did in this work is that, why don't we check what's the current state of each of the computing resources, so going one step below, check the status of each computing resource, and based on that status, we can actually dispatch load. So what we do is like we deploy some agents in each of those computing resources to check their status, and periodically we send back that information to our load balancer, which is in the switch. And based on that status information, and of course based on the load balancing policy, what the load balancer does is like process packet and dispatch to right destination. So this slide is basically trying to say that traditional middle box based on, as I said, at the server level. There are also solutions deployed in the switch, but they don't take care of this computing resource level load balancing. Also, there are some solutions that deployed it to SmartNIC, but we will show that it's not a good idea because SmartNIC cannot process large number of requests the way actually a switch can do. Okay, so this is just to give an idea. So this is the P4 howler architecture. As I was saying, that it has agents that we deploy in every computing resource. It monitors and then gets back to switch with the resource status. Then the data plane component here, what it does is basically, as I said, that it gets this status information and high-level policy, and based on these 2 information, it basically decides where the packet or the request should be dispatched. Okay. Of course, there is detailed underlying complicated architecture, which I don't want to bring here, just giving again the high-level idea. And the controller is the one that decides what should be my load balancing policy. Round robin, ECMP, whatever is the policy, based on that, actually it will configure the data plane switch. Okay? So this is the overall architecture. We implemented and evaluated it for various machine learning applications. And of course, it does a very good job compared to existing solutions. So for example, Cheetah is one existing switch-based load balancer. And we actually have shown that P4 Howler can do very good job in terms of load balancing among these data center resources. And again, the paper is out there. Our Git repo is out there. Feel free to check it. Now, next, I will now switch the gear. So far, I talked about network programmability for security and performance, right? Now, I will show that how AI comes in the scene and can be used also to help you, to help us in terms of performance. So, one lesson that we learned from P4 Howler is that there is no single policy that can actually help you throughout the entire duration of your load balancing, because depending on your load characteristics, depending on the time, actually your demand changes, and then corresponding policy should also change. If it doesn't, then you don't actually efficiently utilize resource and get like expected performance. So what we then thought, that can we consider learning-based policy selection. So depending on the environment, traffic characteristics, load, can we actually choose which policy we have to use, and then use that policy instead of manually setting a policy and then keep using it. So that was the idea. And we were like, okay, which policy we have to use? Let's say we have this P4 Howler. As I have mentioned, that it does a good job, but you cannot use the same policy for various conditions. So we have first checked which machine learning scheme. Would it be like supervised one? The answer is no, because environment change very drastically. If you use supervised one, you have to train model, and you have to retrain again, so on and so forth. So we actually ended up using reinforcement learning and come up with this new system called P4Wise, where we use AI to improve the performance of P4 Howler. Okay, and this is like the architecture where we have again control plane, data plane. The RL agent is the one we deploy in the controller. It gets the network state information from data plane, and the agent gets trained. And based on that training, it specifically tells what should be their policy. And that policy is the one deployed in the data plane for packet processing. And we just show here that if you use individually different policies, like let's say priority, weighted round robin, then as I said, as your load changes, characteristics changes, you will see that your performance won't be at the expected level. But when we use P4Wise, as soon as the characteristic changes, we switch our policy and then maintain expected performance. So this is basically P4Wise. Again, we implemented in real hardware and showed that it does a good job. This is a little bit of details in terms of like P4Wise's agent, which I already talked about. Little details like in terms of what we use in terms of calculating like reward. For example, we use like weight of different resources and their utilization, and we use Q-learning basically, and then train our model. This is just some sample output that when we, as I mentioned, that when we use P4Wise, then we can actually effectively switch between policies and then maintain expected performance. Now, more on AI. Because so far I talked about network programmability and then AI for performance improvement. But then AI can also be used of course, in many other contexts. next one I will show that how AI can be used in telecommunication, particularly in 5G. Okay, so this project I did it with Ericsson, and the motivation or the concept that was there in our mind is that of course 5G is getting mature. It's being deployed successfully in many places, including Canada. And because of this 5G, now we can think of different applications like self-driving cars, AR, VR, mobile gaming, those sort of things, right? Now, but it's like really a complex architecture, and at the same time, it also creates a lot of traffic. So that traffic is something we can exploit to develop learning-based solution, right? So this is just an example that how data is being increased from this 5G environment and how complex is the 5G environment. Now, what we did in this project, we focused on anomaly detection, root cause analysis, which is very common in let's say radio access network in 5G, but it has high impact. Think about like self-driving car. If there is any sort of failure or hiccup, it's gonna definitely impact, right? So what we did in this project is that using the gathered data, we developed a failure prediction model using graph neural network and transformer. So we are the first to actually use this GNN and transformer and predict like 5G radio link failure in radio access network or RAN. So this is the architecture. We have GNN, graph neural network module, that captures the spatial context, okay, surrounding a given link, and then the transformer module, okay, which is basically, so this the left hand side marked by 1 and 3, they are part of this GNN, and then the right hand side here, like particularly it's marked there number 2, basically it is the transformer module. Transformer module is the one that captures the temporal context, because we are talking about the spatial temporal traffic in this 5G RAN environment, because we are getting data from different base stations, so on and so forth, and this traffic actually changes over time. So we developed this model, and this model actually we focus to predict this radio link failure. We also developed a similar GNN transformer with module called architecture called SIMBA for root cause analysis. So some common faults in RAN, can we actually predict those? And the answer is yes. This is the architecture, very similar architecture as I said. And then we focused on this common faults in 5G, like too late handover, inter-cell interference, excessive power reduction. And we did a good job, basically. Both cases compared to state of the art, we did a good job. I don't want to go because I know that maybe there is a time limit. How much time I have?
We have 5 minutes until the next class begins.
Okay.
So perhaps
Then,
on the interest of interaction with the people, I don't know, you can manage the 5 minutes.
I will quickly talk about the next one, where basically, as I said, this is the project going on right now. I'm talking about AI systems now, how to make AI systems sustainable, both in the cloud and in the edge. So this project is going on. I'll just quickly talk about that. This is, for example, a system where first we actually annotate machine learning models, large language models to measure energy, component-wise energy, and then also like in the system level energy, like let's say CPU, memory, GPU energy. And then once we measure the energy, then we can actually use again like a learning-based approach to optimize the energy uses. So that's what we are doing, and then we also did something similar for the edge devices, Raspberry Pi, JSON Nano. In both cases, we actually measured various types of models, measured the energy, and then based on that, now we can move forward and then come up with a system that will actually optimize the energy uses without degrading performance. Okay. Last but not the least, of course, I thank my students, supporter. This is the one I wanted to say that I'm hiring PhD students, 4 PhD students at this moment on these areas, system for AI, big data, and then the smart home security. Please spread out. If anybody is interested, feel free to contact, then we can take the conversation from there. Yeah, I have some concluding remarks which you can read. Yeah, thank you.
We have time for questions, so please feel free to ask our presenter. Luigi.
And feel free to email me here
Sure.
if you want to communicate further.
I have 3 questions. Don't know one after the other, or let somebody else after the first, maybe.
Okay.
Yeah. So, first, thank you very much for being here, and thank you for the nice presentation. It was very, very interesting, all the topics. I have a question about transparency, slide 16. If you can move there, please.
For the sake of time, just quickly go there. Yes, this one?
So from the data center point of view, you know, I was wondering how this scales. Because the problem for me is that the data center has the same problem. They have to schedule their jobs into different machines. Depending on the client, depending on the time of the day, they don't allocate extra hardware for those clients that usually, you know, need the thing at 6 p.m. So that kind of information is already there. And the problem is that you are solving an NP complete problem, which is scheduling. So I was wondering, how do you scale that? How do you see the problem of scaling about using this technique?
Yeah, I mean, in this case, basically we consider, let's say, data center switch that usually connects around 250 servers. So we try to test with this number of switches. So these results that I have shown, this is based on real deployment, right?
Okay.
But we also tested this scale using a simulator, which is basically kind of a realistic simulator. And then over there we tried various number and then showed that, you know, it can actually sustain. And as I said, we are doing it up to 250 with the justification that that's the number of servers a single switch can actually support.
Okay, so switch level, you can
Yes,
see that
yeah.
goes into that. Okay.
Questions? Here, Luciano, and then okay, Mateus.
So it's more a position. I'm sorry for my voice again. So I'm currently a master's student. I'm working with the intersection between software engineering and programmable languages. I would like to just know your opinion about all these techniques. All these papers have excellent solutions, but they lack some kind of methodology that we can bring from software engineering. Like as Professor Luigi said about scalability, modularity, many problems that we face now with programmable modules. I'd like to ask you your position about
From software engineering perspective?
Yeah, how programmable modules benefit if we bring methodologies, software life cycles, safety, predictability about, because it's such a critical infrastructure. I think we could benefit from this intersection.
Very good, interesting question. I have actually a couple of, in fact, the last project that I'm talking about, this edge device, edge environment sustainability. We have a very relevant project that actually recently published. You know, ICSI is going on right now. There is another big conference called MSR, so we published that paper over there. And that project is where we actually consider infrastructure as a code, and then basically come up with some solutions, like there is a specific problem. So what I'm trying to say is, of course, that will be very useful, but I don't think that this area is like new. People have already started, actually. There are some work that people have started working in this aspect. from software engineering perspective. So I would recommend that we can first check a state-of-the-art work if you're really interested and see that where we are right now. Because it's not that you are the one first thought about this. There are some other existing works. But of course it will be useful. There are like some standard methodological aspect in this environment.
Thank you.
Perhaps one final question, Luciano or Luigi?
Hello. Thank you very much for being here at this hack. We're very glad to welcome you. And you know, this programmability thing is sort of lose a bit of momentum. I think a few years ago when Intel decided not to move forward with Tufino, and we have been many discussions on how this area will evolve. Would it go towards like more host-based networking, or maybe there another, I don't know, manufacturer will appear and produce switches? So how do you see the field moving forward in the next 5 years?
Okay. Yeah, that's what I tried to mention, that Oxy already has taken initiative to bring Tufino switch, or P4 switch in market. But another dimension that you have also seen is that other programmable hardware, like a SmartNIC, FPGA, those are actually different edge devices, JSON Nano, for example. Those are actually evolving and kind of giving a paradigm shift in terms of network programmability. Could be like complementary host-based solution, so you are in network and host-based solution in a complementary way. So I feel that that's the area where we are going to see a lot of emphasis in next few years in terms of, especially because network interface card, SmartNIC from like let's say NVIDIA, Mellanox Bluefish, it has like crypto accelerator, it has also AI like TPU. So you see that it has computing power like 16 cores, and also it has like security accelerators, it has AI inference capability. That is something will be a big hype in the next year.
Okay, are you going to be around for the next
Yes,
few
I will
days?
be.
Or-
Yeah, I will be here until end of this week. So feel free to, as I said, just email me, and then we can arrange conversation. I'll be happy to talk.
Great, so let's thank our presenter again. Thank you for being here, and see you in the next
Thank
time.
you everyone for being here and hear my talk.